Okay, so guys, welcome back. Continue section 4.2. I'll do a quick review and continue with the new material we have to cover. So section 4.2 is about shift matrices and circulant matrices. I added a couple of things to the outline. So we talked here about shift matrices, circulant matrices, convolution, and mainly we'll talk today about eigenvalues and eigenvectors of the P matrices matrix and how does this relate to Fourier matrix. And we'll talk at the end about the convolution rule. Okay, so first of all, we presented last time what we call the P matrix, which is a shift matrix, which if multiplied by a vector x, it's in fact, it shifts the order of appearance of the components of x. So you see here that x1, x2, x3, x4 now multiplied by p, okay, becomes x2, x3, x4, x1. This is mainly due to the fact that, in fact, the what was originally the identity matrix, where we had ones in the diagonal, became what we call a shift matrix, where part of the diagonal was shifted to the right side, and the remaining one came in the bottom, at the bottom. Okay, so in fact, the words cyclic and circular apply to P because the first component x1, in fact, is moving to the end. Okay, and if we think of numbers x1, x2, x3, x4 around the circle P, we kind of moving them all by one position. And we computed the P squared matrix, which in fact shifts by two positions every element of x. Okay, now we talked also about circulant matrices. So every new factor P, in fact, gives one additional shift. But if you raise P to the power 4, you have a complete 360 degrees turn. So at size 4, or with size 4, you have always P to the power 4 x equals x. Or in other words, P to the power 4 reproduces I, in fact. Okay, and in general, if you are at working on a size n, you will always have P to the power n, which equals I. Okay, so the next powers, in fact, they repeat the pattern and they cycle around again. So if you can use these P matrices, P, P squared, P3, and P4, which equals I, to kind of build or construct what we call a circulant matrix. Okay, so which has in fact constant diagonal, and you see here it's C0I plus C1P plus C2P squared plus C3 P3. So you see the C0s times I because the C0s appear just in the diagonal. Now C1 times P, here the C1s appear in the upper diagonal, and the last one is at the bottom. And if we shift it again, the P squared would shift again on one position. So we have the C2s here and the C2s here. Okay, and as they see 3 times P to the power 3 here, we're working at size 4. Okay, so you see that the 3 is appearing, the first item appears at the end, and the last and the lower diagonal here. Okay, and each diagonal in that matrix, in fact, cycles around exactly like the ones in P. The diagonal with C1, C1, C1 is completed by the first C1 at the bottom, as we said before. We talked also about what we call cyclic convolution. So what is cyclic convolution? If you multiply two circulant matrices C and D, their product is always it's kind of commutable. So you have CD equals DC. So it's again a circulant matrix. So when you multiply CD, you are multiplying powers of P to get more powers of P, and DC is doing exactly the same. So we did this multiplication. So we took these two circulant matrices. So the first matrix here on the left is C. So we kind of can write it as, in fact, 1 times I plus 2 times P. 2 times P, as you see, this is the P matrix for size 3, and 3 times P squared. And this is you can see that p squared will have 1 here and 2 ones on the lower diagonal. So you will have c, which is I plus 2p plus 3p squared, and multiplied by another circulant matrix, which is 5i, because you see the 5s are on the diagonal, plus 0, in fact 0p plus 4pi squared. Okay, you see the 4 is on the side and on the lower diagonal. Okay, now if you do the math here, if you expand, you are going to end up with 13i plus 22p plus 19p squared. Of course, here, if you are working on size 3, you know exactly that p to the power 3 is exactly I again. Okay, and at the last step, we needed and used the circular effects that p to the power 3 is equal to I, and p to the power 4 will give you again p. So the vectors 1, 2, 3 for C and 5, 0, 4 for D produce the vector 13, 22, 19 for both CD or DC. And that's why this operation on vectors is called cyclic convolution. Okay, so we mainly define convolution on 2 forms, the cyclic convolution and ordinary convolution. So when we multiply n by n circulant matrices, we take the cyclic convolution of the vectors C0, C1, Cn minus 1, and D0, D1, Dn minus 1. Okay, of course, these coefficients are supposed to be distributed on the I, p squared till p to the power n minus 1. Okay, and ordinary convolution finds the coefficients when we multiply the 2 circulant matrices by each other. And the cyclic convolutions use the crucial fact that p to the power n is I. So the ordinary convolution is what we, as we defined, as we talked about it before, is what we studied in 2nd grade. So it's the multiplication you learn in the 2nd grade, and it's made easier because there is no carrying to the next column. So in fact, you will have 1, 2, 3 multiplied by 5, 0, 4. And if you don't carry to the next column, you get 5, 10, 19, 8, 12. Okay? While cyclic convolution gives you exactly what we had in the previous slide. Okay? A practice now we have here. I would like to work it out with you. So I would like you to think about how can one do this multiplication. Okay? This cyclic convolution. Okay, so I'll share with you my whiteboard here, and I'll work it out with you. So, so we have here 0, 1, 0. So basically here, what does 0, 1, 0 mean? It is 0i, okay, plus 1 times p plus 0 times p squared. Okay, so basically just the p matrix of size 3. So basically we're going to have the diagonal which is completely filled out with zeros. We have 1, 1, we have 0 here, we have zeros here, and the last item would carry a 1 here. Okay, so this is the 0, 1, 0 in fact. Okay, now if I'm multiplying by d0, d1, d2, what is d0, d1, d2? Basically, should have written it as d0i plus d1p plus d2p squared. Okay, so you can imagine that we're going to have this following matrix. If we do the math correctly, we're going to have in the diagonal, what should we have on the diagonal? We should have the d0s on the diagonal, right? Because we have d0 times I. Okay. Now the d1s would appear following the pattern we see in P. So we'll have the d1s here. And the remaining items are d2s. Okay. Now let's do the product. Okay. So if you multiply these two by each other, we're going to have the following. So, of course, there is a shift here because you're multiplying by the shift matrix P. Okay, so what's going to happen? You see that the second row would normally should appear in the first row because you're multiplying by 0, 1, 0. So you should get D2, D0, D1. Okay. Then the last row in D would shift to an upper position. So you will have D1, D2, D0 because simply you multiplied by shift matrix, and the first row would become the last. Okay. So in other words, what did you obtain here? You obtained D2I plus D0P, okay, plus D1P squared. Or what you can write also as D1, D2, D0, D1. Okay? Is that clear, guys? Any question on this? So this is first for the first practice. Okay, to do this correct cyclic convolution product. Is it okay? So in the textbook, just I would like to add a small note. In the textbook, there is a small mistake. They don't exactly write the following product. Okay, you can check it again and check by yourself. Okay, so I will go back to the slides right now. So here we go again. So we worked out the practice, the first practice question here, the first one. And if you do the second one, where you multiply 1, 1, 1, in fact, multiplying I plus P squared by D0, D1, D2, you get the first row would be the first row would be represented by D0, D1 plus D0 plus D1 plus D2, D0 plus D1 plus D2 here, and D0 plus D1 plus D2. Okay. Now, if you do the last one, this is more interesting. If you multiply C0, C1, C2 by D0, D1, D2, you get exactly that rule, which meant that CD is equal to C to DC for circulant matrices. And in fact, you can write that the C times D is equal to D times C, following the cyclic convolution rules. Okay, so for cyclic convolution, there is a missing word here. Okay, now in fact, what happened here is that powers of P in C commute with powers of P in D, and there is a kind of magic trick here. Okay, you can have the fun or the pleasure to dig on it. If you take 1 plus 2 plus 3, which appeared in the previous example, which should give 6. Okay, and you multiply it by 5 plus 0 plus 4, which gave 9, you have quick check on convolution. So in fact, if you multiply 6 times 9, you get 54. And that same 54 is exactly the sum 5 plus 10 plus 19 plus 8 plus 12. You got with the ordinary convolution. And that same 54 is exactly the sum you get with 13, 22, 19 with a cyclic convolution. Okay. See? So in fact, this is not magic at all, but because it's the sum of the C's times the sum of the D's equals the sum of the outputs, in fact. And that is because every C multiplies every D in C by the ordinary convolution times D, and C by the cyclic convolution times D. Okay? So it's kind of, it appears like magic, but it's just simple mathematics. Now, I'd like to continue with the new material, and this is how the material we are seeing in section 4.2 relates to the material we're seeing in section 4.1. And this is why, in fact, we shouldn't skip any section in this chapter at all. So now, let's try to compute the eigenvalues of this shift matrix P. So with n equals 4 at size 4, if you would like to find the eigenvectors or the eigenvalues, we need to solve Px equals lambda x. And this leads directly to 4 eigenvalues and eigenvectors. So Px this is the shift matrix times x. So it gives you that first shift we got, and this should be equal to lambda times our x. Okay. So if you work upwards, in fact, what does it mean? It means that x1 equals lambda x4, okay, which equals lambda square x3, which equals lambda cube x2, which equals lambda 4 x4. So at the end of the day, what you have is that lambda to the power 4 should be upstairs here. Lambda to the power 4 should be equal to 1. And that means that you have 4 possible values for lambda on the complex set. So either lambda is equal to I, lambda is equal to I squared, lambda is equal to -1, or what is it? Yeah. Lambda equals to I squared is equal to -1, or lambda equals to I cube, which is this should be minus I guess. This should be minus I. This is a mistake. And the last one is, so these are the 4 eigenvalues. Sorry for that, these types, guys. So the eigenvalues, in fact, you can find are I minus 1, minus I, and 1. And as you might observe, they're equally spaced around the unit circle in the complex plane. So you place 1 here, you place I here, you place the -1 here, and you place a minus I. Okay. Now, immediately you can translate this to the general case, where if you have a generalized n, what happens? You're going to place these eigenvalues. Every lambda is going to be equal to what? To e to the power 2 pi I over n. Okay, that is the missing line here. I'll try to put it right back in the after the class. Okay, so and generally this is what you get. Okay, now does this remind you of something? It's up to you guys. Does this remind you the form or the shape of these eigenvalues? Does it remind you of something you've seen recently? Nothing at all? Okay, so let me continue then. So in fact, the solutions, they all share this, they are all solution to z to the power n equals 1. And you can write lambda as w squared till w to the power n minus 1. And in general, this is the form of w, which is e to the power 2 pi I over n. So now knowing the n eigenvalues, we can find the n eigenvectors. So if you solve the eigenvector problem and you set the first eigenvector to just once, as you see here, this is Q1, the other components would appear immediately to the next eigenvector. So this is going to be Q2, Q3, and Q4 because we are working on size 4. And immediately, this is the Fourier matrix of size 4. Okay? So you see that the Fourier matrix of size 4 is exactly the eigenvector matrix for our shift matrix. And you can easily check that the conjugate of F transpose multiplied by F gives you for I, or in general, you can say that the conjugate of F times F gives you Ni. Okay? And the pattern is the same for any n. The eigenvector matrix is exactly the n by n Fourier matrix with F conjugate transpose times F, which gives you Ni. So you see now how beautiful it is that the eigenvectors of the shift matrix is in fact the eigenvector matrix of the shift matrix is the Fourier matrix. And the eigenvalues of the shift matrix are in fact these W's we've considered in the 4.1 section. Okay. Now, what about circulant matrices? For a circulant matrix, C, of course, we said that what is a circulant matrix? Again, a reminder, a circulant matrix is composed of powers of P. So C is in fact C0I, C1P, plus, and on the next position you have C2P squared, till you reach the last item, which be Cn minus 1, because you start with C0, P to the power n minus 1. Okay, so this is a circulant matrix. So for a circulant matrix, we have an almost also magical formula. If you multiply f by the vector c, we just chosen here, c0, c1, c2, cn minus 1, okay? And the top row of c, you can find the eigenvalues. So in fact, each one of the eigenvalues of c corresponds to just the result of the multiplication of f by c. So the first eigenvalue of the circulant matrix would be C0, the sum of all the coefficients. The second eigenvalue would just place W, okay, after C1, then W to the power 2 after C2, till you reach the last item, which is Cn minus 1, where you place W to the power n minus 1. If you move to the next eigenvalue, you now raise every item here to the power 2. Okay. Now, if you roll on till you reach the last eigenvalue, you multiply every one by W n minus 1 times. Okay. So you see how you see the pattern. So there is a magical formula to obtain the eigenvalues of the circulant matrix using these C components. Okay. In fact, it's just the result of the multiplication f by c, of the Fourier matrix by c. So the n eigenvalues of c are the components of this product, f by c. Okay. Or what we also call the inverse Fourier transform of c. And for any n, the permutation p, in fact, is a circulant matrix C with C equals 0, 1, 0, 0, 0, of course. This is so the permutation is just a particular case where the second component is 1. So you just take C1p and all others are 0. So the eigenvalues of p, in fact, are in the column vector fc with this c. That is the column 1 w squared till w to the power n minus 1 of the Fourier matrix f. Okay? So you see now how beautiful it is, how the eigenvalues and eigenvectors of shift and circulant matrices, they do appear. Okay? Let's work a small example here. So let me take the example where n equals 2. Okay? And of course, here, if we can consider that n is equal to 2, the w, there is a small typo here again, we have 2 pi I over 2, which is going to be w, okay, in the Fourier matrix f. So if n is equal to, the shift matrix would be written this way. Okay, there is no other way to place these ones. So p would be 0, 1, 1, 0. Okay, and let's consider this shift matrix, this circulant matrix, where we have just C0, C1. So you have the C0s are placed on the diagonal, and you have C1 and C2 on the anti-diagonal. So basically, C is in fact equal to C0 I plus C1. Okay. So now, if you take these components, C0, C1, you have the C vector, which is C0, C1. Okay? And the corresponding Fourier matrix. Now, we have the general form for it. What is it? So, if you are working on size 2, F would be, as we've seen in section 4.1, the first column is 1s, then you have 1, and here we'll have just I squared. Okay? So, and you know I squared is just -1. So that's why you have -1. Okay. So the eigenvectors of P now, and also of C, are the columns of F. So the eigenvectors of P, this matrix, the shift matrix, and of C are here, are 1, 1, 1 minus 1. You can check it. Okay. Whatever are the values of the coefficients C0 and C1. Okay. Moreover, this is for the eigenvectors, and for the eigenvalues of P, the eigenvalues of P are plus or minus 1, while the eigenvalues of C are going to be following the magical formula we've seen in the previous slide. So you will have the first one will be C0, C1 plus C1, and the next one will be just C0, minus C1, because you have C0 for this one plus C1 times I squared. Okay? So times minus 1. Okay? And these eigenvalues of C, in fact, are the components of F times C. Okay? So if you do the product, you can just verify that F times C, well, you don't need to solve here the eigenvalue problem for C, for the circulant matrix C. You just need to multiply F by small c to get these eigenvalues. Okay, so now how can one ask a question about this? So if we are having a circulant matrix, let's suppose I'm giving you a circulant matrix C, and I'm asking you to compute the eigenvalues. There are two ways to go. There is the old way, which consists in finding what, guys? Remind me, please. How do we find the eigenvalues of C? We just saw the determinant of C minus lambda I equals 0, right? That's the old-fashioned way, right? Or the common general way for any matrix. Now, of course, for any square matrix, I'm sure. So now, if I'm having a circulant matrix, what can I do? To find the eigenvalues, I just need to compute the product F by C. Okay? Of course, now I need to understand what is the corresponding Fourier matrix of the same size as our circulant matrix. Okay? So you need to multiply Fn by C. Got it, guys? Any question on this? Clear? Okay. So be careful. If the question is about there is a shortcut here, if you have a circulant matrix, then it's much easier to get the eigenvalues by multiplying the Fourier matrix of the same size by just the components of C. Okay? Now, let's talk now here about the convolution rule. And this rule is this rule compares, in fact, convolution with multiplication. So let's be clear, they are quite different. Convolution is not multiplication, okay? But they are beautifully connected using that Fourier matrix F. So if you start with two circulant matrices, C and D, and of course, we've seen that their top rows are usually indicated by small c and small d, okay, as we've seen in the previous examples. So, and at the start of this section, we've shown, there is an example that showed that the top row of CD gives a cyclic convolution, and it's equal to C times D with a cyclic convolution, okay, or what we call the cyclic asterisks. Then the eigenvalues of CD, in fact, according to that equation, which equation? Equation 14. And now what is equation 14? In fact, we've seen it just a little bit before that one, the one that allowed it to find the eigenvalues of the circulant matrix. So the one that writes the, let's say, the lambda vector as FC, okay? So lambda here, capital lambda, is the lambda, the eigenvector, the eigenvalue vector, not the eigenvector, the eigenvalue vector of our circulant matrix. Okay. So let me write it again here, so I can carry it with me. This is a typo, of course, I corrected. So the equation 14 here, what did it write? It showed that the capital lambda of C, of the circulant matrix, is in fact F by times small c. Okay. So just remember it here. So the eigenvalues of CD, according to that equation, are in the vector F multiplied by C multiplied by D, by the cyclic convolution. Okay. Now, what about if you apply 14 to CD, guys? If you apply 14 to CD, you'll get capital lambda of CD would be F by C times D by the cyclic convolution. Okay. this is what we are trying to say. Okay. So we can find these eigenvalues, in fact, another way, and show again that, in fact, this is what we can call the Hadamard product. So, in fact, lambda k of CDs, or the lambdas of CD, is just the lambda k of C times the lambda k. And the convolution rule, in fact, compares our two formulas for the C. So you can define the convolution rule as follows. So f of C times D is f of C times f of D. Now, this dot to the power star here, or is in fact this distributed product, or the product item by item, what we call also the Hadamard product. With MATLAB, this is the way to know it, okay? Hadamard product. I'll give you a quick example, okay, of the Hadamard product. So I'll give you a small example. This is what we are trying to say here. I'll share with you my whiteboard right now. Okay, so what we were just saying is that the eigenvalues of CD, okay, or the kth eigenvalue of CD is in fact the kth eigenvalue of C multiplied by the kth eigenvalue of D. Okay, so this is what we've just shown. Okay, so in fact, you can, in matrix form, it means that F multiplied to C times D with the cyclic convolution. I'll use the small ones, okay? Okay. Is FC, it is F multiplied by C with the Hadamard product times 8. Okay. So as an example, let's say that I got these eigenvalues. I have 1, -1, and 2 as eigenvalues for C. Okay, so these are the lambda C's. And I got I'll do the Hadamard product. Okay, these following eigenvalues for D. I'll say here I'll get I minus I, and say I have let's say I have just 1. Okay, what is the result of the Hadamard product? It's just product item by item. So we have I, am I right? So 1 times I, minus 1 times minus I is I itself, and I'll have 2 times H just 2. Right? So let me say that if you have a matrix C, capital C, with such eigenvalues, 1, minus 1, 2, and another matrix, capital D, with such eigenvalues, I, minus I, and 1, then the result is that the product CD has the following eigenvalues: I, 2. Okay, which is again by the convolution rule is again another shortcut to get the eigenvalues if you have a product of 2 circulant matrices. Got it, guys? So this is the interest of seeing such things. So the interest of seeing such things is to save time in case you have shift matrices, circulant matrices. It's saving time with the computation of what? Of the combination of the eigenvalues and eigenvectors. Got it, guys? Okay. So basically, this is all for today. So I'll stop the recording right now. If you have any questions, let's